Most people, when they think about space, are thinking about the wrong thing. The image most of us carry is something like this: Earth, then the moon, then some darkness, then Mars, then more darkness, then Jupiter, and so on until things get vague and distant. This is the solar system. It is the version of space that appears in textbooks and on the walls of elementary school classrooms, and it is genuinely vast by any human standard. Light takes about 8 minutes to travel from the Sun to Earth. It takes roughly 4.5 hours to reach Neptune. By the time you reach the edge of the solar system, you are already in territory so remote that the Sun looks like a very bright star, nothing more. Most people would call that deep space. Most people would be wrong. What lies beyond the solar system is not more of the same. The distance from Earth to Neptune is roughly 4.5 billion kilometers. The distance from the Sun to the nearest star system, Alpha Centauri, is about 40 trillion kilometers. That is not a mild increase in scale. That is a jump of nearly 10,000 times. The entire solar system, every planet, every moon, every asteroid, every comet, shrinks to a single point against the backdrop of interstellar space. Then interstellar space itself, the region between stars within a galaxy, shrinks to a single point against the backdrop of intergalactic space. And intergalactic space, as staggering as it is, shrinks to nothing against the scale of the voids between galaxy clusters, the largest structures in the known universe, some stretching hundreds of millions of light years across. This is where deep space actually begins, not at the edge of the solar system, not at the edge of the galaxy. Deep space is the space that dominates the universe. Almost all of the universe's volume is made of this. The intergalactic voids, the stretches between galaxy clusters, the regions so remote that the nearest galaxy is not a smear of light in the sky, but a single dim point separated from you by distances your brain is not built to hold. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Here is the thing that changes everything. Deep space is not empty, not in the way the word empty usually means. The vacuum between stars contains roughly 1 hydrogen atom per cubic centimeter. Drop to intergalactic space, and that number falls to about 1 atom per cubic meter. In the deepest voids between galaxy clusters, it falls further still. The air you are breathing right now holds approximately 30 quintillion molecules per cubic centimeter. Deep space holds almost nothing. But almost nothing is not nothing. That distinction matters enormously. The universe is threaded with thin gas, charged particles, magnetic fields, radiation. There is structure to this near emptiness. There are temperatures, pressures, particle flows, fields that behave in ways that have no parallel in anything we encounter on Earth. The rules change out there. Things we take for granted, the way heat moves, the way radiation works, the way the human body functions, none of these assumptions survive intact once you leave the thin shell of space that surrounds our planet. The cosmic microwave background radiation fills every cubic centimeter of the universe with a faint glow at 2.7 degrees above absolute zero. Galactic cosmic rays, particles accelerated to nearly the speed of light by supernovae and other violent events, stream through deep space in every direction. Near a neutron star, the magnetic field is so intense it would restructure the atoms in your body. Inside a black hole, time and space swap roles. These are not poetic descriptions. They are the physics of where most of the universe's volume actually is. Almost everything we know from lived experience stops being a reliable guide once you go far enough. This is not a small thing to sit with. It means that our intuitions about distance, temperature, pressure, time, and matter were built entirely within a thin, warm, sheltered corner of a galaxy that represents a fraction of a percent of the universe's volume. Step outside that corner, and the rules do not bend. They break. What happens in deep space has no simple answer. It is a different kind of answer for each of the different environments out there. The interstellar medium between stars, the intergalactic medium between galaxies, the near vacuum of the great voids, the extreme neighborhoods of the densest objects in existence. The story of deep space is not a single story. It is several stories layered on top of each other, and every one of them is stranger than the pictures we grew up with. The real deep space, the one that makes up almost all of the universe's volume, operates by rules that nothing in human experience has prepared you to understand. The vacuum of deep space is not a single thing. That is the first mistake most people make when they try to picture it. They imagine a uniform darkness, a featureless nothing that stretches from the edge of Earth's atmosphere all the way out to the farthest reaches of the universe. The reality is more structured, more strange, and in some ways more unsettling than that. Start with what you already know. The air around you right now contains roughly 30 quintillion molecules per cubic centimetre. That number is so large it barely registers. 30 quintillion. Written out, it is a 3 followed by 19 zeros. Every breath you take pulls billions of those molecules into your lungs. The air feels like nothing, like pure emptiness, because human senses were never built to detect individual molecules. But the air is almost unimaginably crowded compared to what lies beyond Earth's atmosphere. Drop down through the layers. At the edge of Earth's atmosphere, the pressure is falling fast. By the time you reach the altitude where space officially begins, about 100 kilometers up, the air is already so thin that conventional aircraft cannot generate lift. Keep going. A few hundred kilometers higher, where the International Space Station orbits, the pressure has dropped to something like 1/10 trillionth of what it is at sea level. This still does not qualify as a hard vacuum. There are still stray molecules up there, still enough atmosphere to slowly drag the station down over time, which is why it needs periodic boosts to maintain altitude. The vacuum of low Earth orbit is not the vacuum of deep space. Move outward, into the interplanetary medium, the space between the planets inside our solar system. Here the pressure drops another several orders of magnitude. The dominant presence is the solar wind, a constant stream of charged particles flowing outward from the sun. But even that is extraordinarily diffuse. The density of the interplanetary medium near Earth is roughly 5 to 10 particles per cubic centimetre. Not molecules, particles, mostly protons and electrons. Compare that to the 30 quintillion molecules per cubic centimetre in the air around you. The difference is so large that the word thin does not come close to capturing it. Now go further, past Neptune, past the edge of the solar system, through the heliopause and into the interstellar medium. This is the gas and dust that fills the galaxy between star systems. The density here drops to roughly 1 hydrogen atom per cubic centimetre. 1. where the air around you contains 30 quintillion molecules per cubic centimeter. The space between the stars contains one atom. The gap between those two numbers is the gap between everything you have ever experienced and something your intuition has no framework for. And that is not even the bottom. Travel out of the galaxy entirely into the intergalactic medium between galaxies. Here the density falls by another factor of 1,000,000. One hydrogen atom per cubic meter. A cubic meter is roughly the size of a large microwave oven. One atom in that entire volume. The pressure at this point is so low, it is measured in values like 10 to the power of -17 atmospheres. Numbers that only exist in physics textbooks, that have no equivalent in any human scale experience. The deepest cosmic voids, the enormous empty regions between galaxy filaments, go lower still. The density there approaches values so small that calling it one atom per cubic meter would be generous. This is not empty in the way a vacuum-sealed jar is empty, or the way a room with the air pumped out is empty. This is emptiness at a scale that has no earthly comparison. It is the universe offering you the closest thing it has to pure nothing. What does this structure mean in practice? For physics, the answer is significant. Friction requires medium. It requires particles to push against, surfaces to grind against, something to resist motion. In the interplanetary medium, there is almost none. In the interstellar medium, even less. In the intergalactic voids, essentially zero. This changes the rules of motion entirely. On Earth, a thrown object slows down because it is constantly colliding with air molecules, transferring energy with every collision. In deep space, a moving object collides with almost nothing. There is no force to slow it. This is not a small difference. A spacecraft coasting through interstellar space is not slowly braking. It is not losing speed to friction. It will maintain its velocity essentially forever, or until gravity from some nearby object acts on it. Voyager 1, launched in 1977, has been coasting for decades and is still moving at roughly 17 kilometers per second. No engine, no fuel burn, just the initial velocity from its launch and a few gravitational assists from the outer planets, and then nothing to slow it down. The vacuum provides no resistance because there is almost nothing there to resist against. For light and radio waves, the vacuum behaves as a nearly perfect medium for transmission. Signals from Voyager 1, now billions of kilometers away, still reach our antennas because nothing in the interplanetary and interstellar medium is dense enough to absorb or scatter them significantly. The faintness is a problem of distance and power, not of absorption. Light from galaxies billions of light years away crosses intergalactic space and arrives at our telescopes because that space is so empty that almost nothing gets in the way. For spacecraft design, the vacuum creates its own challenges. Without air, there is no convective cooling. Heat generated by electronics has no medium to dissipate into. It can only radiate away, which is slow. Engineers designing deep space probes spend enormous effort on thermal management because the vacuum is not a neutral environment for heat. It traps it on the sunward side and radiates it slowly from the dark side, creating temperature extremes on the same object simultaneously. The vacuum is not uniform, it is not neutral, and it is not nothing. It is a physical environment with measurable properties that vary across 10 orders of magnitude of density, depending on where in the universe you happen to be standing. In the deepest voids between galaxy clusters, A spacecraft could travel for billions of years without hitting a single atom, and nothing in the physics of the situation would stop it from doing exactly that. Space is not cold the way a winter night is cold. A winter night is cold because air molecules are moving slowly and pulling heat away from your skin through conduction. Deep space has almost no molecules at all. There is nothing to conduct heat anywhere. The cold of deep space is a different kind of cold entirely, and understanding it requires letting go of almost everything ordinary experience has taught you about temperature. The baseline temperature of deep space is 2.7 Kelvin. That is roughly negative 270 degrees Celsius, just barely above absolute zero, which is the lowest temperature theoretically possible anywhere in the universe. But here is the part that surprises most people. That number is not the temperature of emptiness. It is not the temperature of nothing. It is the temperature of something specific and real, a form of radiation that fills every single cubic centimeter of the observable universe without exception. The 2.7 Kelvin figure is the temperature of the cosmic microwave background, the faint afterglow of the Big Bang itself, stretched thin across 13.8 billion years of cosmic expansion. Everywhere you look, in every direction, that radiation is present. It passes through walls. It passes through planets. Right now, roughly 400 photons of it occupy every cubic centimeter of the room around you. This matters because it means absolute zero is unreachable. Not just difficult to reach, structurally, physically, fundamentally unreachable anywhere in the universe, because the cosmic microwave background is always there, always delivering tiny packets of energy into any object it touches. An object cooling in deep space will approach 2.7 Kelvin. It will slow down as it gets closer. But the CMB photons keep arriving, keep depositing energy, and the cooling stops. The floor has been set. The universe will not let anything go colder than its own background temperature, and that background temperature is 2.7 Kelvin. Think of it like a room that can never be made completely dark because the walls themselves are faintly glowing. You can dim every lamp you have. You can block every window. But the glow from the walls is always there, and no matter what you do, that glow will always reach your eyes. The CMB is the glow in the walls of the universe. Now consider what happens near a star. The temperature in the corona of our own sun reaches several million degrees Celsius. The surface itself sits around 5,500 degrees. Move a few light minutes away, and temperatures in the solar wind still run into the tens of thousands of degrees for individual particles, even though the density is so low that a thermometer placed there would actually read cold, because so few particles are hitting it. Temperature and heat are different things in near-vacuum environments, and the distinction becomes important fast. But the point holds. The universe does not have a single temperature. It has a baseline, and then it has regions of violent, lethal exception. A rock in deep space, far from any star, will cool toward that 2.7 Kelvin floor. The side facing nothing will radiate heat slowly outward into the CMB bath. Given enough time, it settles. But the same rock positioned near a star faces conditions that split along a sharp line. The sunward face, with no atmosphere to distribute heat and no air to carry it away, bakes. Temperatures on the sunlit surface of Mercury reach around 430 degrees Celsius. The shadow side of Mercury drops to negative 180 degrees. Same rock, same moment, two temperatures separated by a few feet and a shadow line. There is no medium to equalize them. The heat cannot flow through air because there is no air. It can only radiate, slowly, and in vacuum that process takes much longer than intuition suggests. A human body unprotected in deep space would lose heat through radiation alone. In normal environments, you lose heat through conduction and convection, warm air rising off your skin, contact with cooler surfaces. None of that exists in vacuum. Radiative cooling is slow. You would not freeze in seconds. Your body would continue generating its own metabolic heat for a short time. The moisture on your eyes and the surface of your skin would evaporate. But the temperature of deep space would not claim you quickly. Other things would claim you much faster. Oxygen deprivation would render you unconscious in roughly 15 seconds. The cold would be a background process, working gradually on a body that had already stopped functioning for other reasons entirely. Eventually, given enough time with no star nearby, a body drifting in interstellar space would cool toward 2.7 Kelvin. It would never quite arrive. The CMB would hold it just above the floor. The other extreme is equally strange. Astronauts in low Earth orbit, in full sunlight with no atmosphere to filter it, face solar radiation intense enough to heat exposed surfaces above 120 degrees Celsius. Simultaneously, anything in shadow can drop to negative 160. Their suits are engineering problems of considerable difficulty, precisely because both conditions must be managed at once, continuously, across a thermal gradient that no environment on Earth ever produces. The boundary between lethal heat and lethal cold in space is not a zone, it is a line. One side of a spacecraft in direct sunlight and the shadow side of the same spacecraft exist in what might as well be two different worlds. Nothing in human thermal experience maps cleanly onto this. On Earth, heat distributes. Convection carries warmth from sunny spots into shaded ones. Air mixes. Temperatures even out over time. In space, what the sun touches gets hotter. What it misses gets colder, and between those two conditions there is almost no communication. A spacecraft sitting in intergalactic space with no star nearby would eventually settle toward 2.7 Kelvin, and there it would stop, held just above absolute zero by photons that have been traveling since before the Earth existed. In 1964, two radio astronomers working with a large antenna in New Jersey could not figure out why their equipment kept picking up noise they could not get rid of. Arno Penzias and Robert Wilson had built a sensitive receiver meant to track satellite signals, and everywhere they pointed it, regardless of direction, a faint, stubborn hiss persisted. They checked the hardware. They rechecked the calibration. Then they found pigeon droppings inside the antenna horn and cleaned them out carefully. The hiss remained. It was coming from everywhere at once, with the same intensity in every direction, at every hour of the day, in every season. That uniformity was the clue they did not yet know how to read. What they were hearing was the oldest light in the universe. To understand what the cosmic microwave background actually is, you have to go back to a time before stars existed, before galaxies existed, before any structure in the universe existed at all. In the first 300,000 years after the Big Bang, the universe was not the cold, dark, mostly empty place it is today. It was a dense, blindingly hot plasma, a churning mixture of protons, electrons, and photons so tightly packed and so energetic that light could not travel more than a short distance before colliding with a charged particle and being scattered again. The universe was opaque. Not dark exactly, more like the inside of a sun, bright everywhere and impenetrable. Photons generated in those early moments were not free. They were trapped, bouncing endlessly through the plasma-like sound waves trapped inside a sealed room. Then something changed. As the universe expanded, it cooled. After roughly 380,000 years, the temperature dropped to around 3,000 degrees Kelvin, cool enough for electrons to slow down and bind to protons, forming the first neutral hydrogen atoms. This transition took place across a relatively short window of cosmic time, and its consequences were immediate and total. The fog lifted. Suddenly, photons that had been scattering continuously for 300,000 years had nothing left to bounce off of. The universe became transparent in what astronomers call recombination, and all that trapped light streamed outward in every direction at once. A wall of light expanding across the entire universe simultaneously. That light has been traveling ever since. The universe has expanded enormously in the 13.8 billion years since recombination, and expansion does something specific to light. It stretches its wavelength. Photons that were released as high-energy visible and ultraviolet radiation have been stretched by the expansion of space itself, pulled from short, energetic wavelengths down through infrared and into microwave wavelengths over billions of years of travel. What was once a blaze of visible light, equivalent to a stellar atmosphere, now arrives as a faint glow at just 2.7 Kelvin. The energy is still there. It is just spread across much longer wavelengths, which is why the signal that Penzias and Wilson detected was a microwave hiss rather than visible light. They were listening to a fire that had cooled across 13 billion years of cosmic expansion. When physicists confirmed what Penzias and Wilson had found, the magnitude of the discovery was difficult to overstate. This was not a signal from a star or a galaxy. It was not radio interference. It was the direct thermal afterglow of the Big Bang itself, now filling every cubic centimeter of the observable universe with roughly 400 photons. Penzias and Wilson received the Nobel Prize in Physics in 1978. The antenna still stands in New Jersey. What makes the CMB remarkable is not just its age, it is what it contains. When astronomers began mapping the CMB with greater and greater precision, they found that it was not perfectly uniform. There are tiny variations in temperature across the sky, fluctuations of roughly 1 part in 100,000. So small they are nearly undetectable. Nearly. These fluctuations represent real differences in the density of matter in the early universe. Some regions were infinitesimally denser, some infinitesimally thinner. In any ordinary circumstance, those differences would mean almost nothing. But gravity is patient. Over hundreds of millions of years, the slightly denser regions pulled in surrounding matter, growing denser still, attracting more, collapsing eventually into the first stars and galaxies. The thin regions expanded further, becoming the voids that now stretch hundreds of millions of light years across. Every structure in the observable universe, every galaxy cluster, every filament of the cosmic web, every star that has ever burned, traces its origin back to fluctuations that were already baked into the universe before it was 1 million years old. This is what the CMB actually is. It is not background noise. It is a photograph of the universe at the moment it became transparent, printed in microwave light, stretched across the entire sky. The temperature variations in that map are the blueprint for everything that followed. Cosmologists use it to measure the age of the universe, its geometry, its composition, the relative amounts of ordinary matter and dark matter. All of that information is encoded in fluctuations smaller than the width of a human hair compared to the height of a skyscraper. Every direction you look in the microwave sky, you are seeing a snapshot of the universe as it was 380,000 years after the Big Bang. And the tiny ripples in that image are the direct ancestors of every star, galaxy, and cluster that has ever formed. The space between stars is not empty, and the difference between that statement and what most people picture is significant enough to be worth sitting with for a moment. When astronomers talk about the interstellar medium, they are describing something that sounds modest on paper. A thin mixture of gas and dust distributed across the vast distances between star systems. The numbers at first seem to argue against importance. 1 hydrogen atom per cubic centimetre on average. Compare that to the air in this room, which contains roughly 30 quintillion molecules in every cubic centimetre, and the interstellar medium sounds like nothing worth discussing. But that framing is wrong. The interstellar medium is not the gap between the interesting parts of the galaxy. It is the substance from which every interesting part was made. The composition breaks down simply. About 75% of the mass is hydrogen. About 25% is helium. Everything else, every heavier element in the periodic table, accounts for a fraction of a percent by mass. Trace amounts. But those trace amounts include carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements that eventually become planets, oceans, atmospheres, and living things. The interstellar medium is not pure. It is contaminated, in the best possible sense, by the wreckage of every star that has ever died. What makes this medium genuinely strange is that it is not one thing. It exists in several distinct phases, and those phases share the same galaxy without ever fully mixing into a single uniform state. The coldest phase is the molecular cloud. These are dense regions, dense by interstellar standards, where hydrogen atoms pair into molecules and temperatures drop to somewhere between 10 and 30 degrees above absolute zero. These clouds are dark. They block the light of everything behind them. From the inside of a molecular cloud, if you could survive inside one, visibility would be essentially zero. No stars, no background glow, just cold, slow, drifting molecules. These are also the places where gravity eventually wins. When a molecular cloud grows dense enough, clumps within it begin to collapse under their own weight. The collapse accelerates, the center heats up, a protostar begins to form. Molecular clouds are not quiet, they are nurseries. The stars being born inside them right now will outlive everything currently alive on Earth by billions of years. Outside the molecular clouds, spread more evenly through the disk of the galaxy, is warm neutral hydrogen. Temperatures in this phase run somewhere between a few thousand and about 10,000 degrees. That sounds hot, but the density is so low that the actual energy content is minimal. A human hand passing through it would feel nothing. The gas is too thin to transfer heat in any meaningful way. This warm neutral phase is the background fabric of the galaxy's interior, filling the volume between denser structures the way water fills the space between stones on a riverbed. Then there is the hot ionized phase. Near massive young stars and near the expanding shells of supernova remnants, temperatures climb into the millions of degrees. The hydrogen is no longer neutral. The electrons have been stripped away by the energy of nearby events, and the gas glows. These regions are the ones that show up in photographs as coloured nebulae, emission clouds radiating at characteristic wavelengths that different elements produce when their electrons fall back into lower energy states. The red in most nebula photographs is hydrogen. The blue-green tones are often oxygen. Every coloured cloud in a deep sky photograph is the interstellar medium made visible by energy borrowed from a nearby star or explosion. These phases coexist in a state of constant slow exchange. Supernova shockwaves plough through cold molecular clouds, compressing them on one side and heating them on another. Radiation from newly formed massive stars carves ionized bubbles into surrounding neutral gas. Stellar winds push outward and gradually thin the regions around young stars. The interstellar medium is not static. It is a slow, continuous cycle of matter being heated, cooling, condensing, forming stars, being expelled again, and beginning the process over. The dust embedded in this medium is worth its own attention. Interstellar dust grains are tiny, far smaller than the particles in household dust, typically a fraction of a micrometer across. They are made of silicates, carbon compounds, and ices of various kinds depending on their environment. Individually, they are nothing. Collectively, they are formidable. A dense molecular cloud can block virtually all optical light, making it impossible to see through with a conventional telescope. The dark patches visible against the bright band of the Milky Way are not gaps in the stars. They are dust clouds sitting between us and the stars behind them, absorbing and scattering the light before it can reach us. Infrared telescopes cut through this barrier easily. Infrared light has a longer wavelength and passes through dust grains with far less interaction. Much of what we know about star formation comes from infrared observations, because the most active sites of new star birth are buried deep inside the clouds that hide them from optical view. The dust grains also serve a chemical function. On their surfaces, molecules form that could not assemble in the gas phase. Complex organic molecules, some of the precursors to biochemistry, have been detected in molecular clouds because the grain surfaces provide a place for atoms to stick and react slowly over millions of years. The interstellar medium is not chemically inert. It is a slow-motion laboratory operating across distances that make the distance from Earth to the Sun seem trivial. Every atom that entered our solar system when it formed came through the interstellar medium. The molecular cloud that collapsed to form the Sun and its planets had already been enriched by several generations of stellar death. Elements forged in stellar cores, distributed in supernova explosions, processed through the medium, reincorporated into new clouds, expelled again, mixed again. This cycling has been running for most of the galaxy's history, and the result is sitting in the periodic table. Every atom of iron in your blood was forged in the core of a dying star, ejected in a supernova, drifted through the interstellar medium for millions of years, and ended up as part of you, a fact that is either beautiful or unsettling depending on your mood. At this moment, the sun is blasting a 1,000,000 miles per hour stream of charged particles outward in every direction, and those particles are moving through the solar system right now, past the Earth, past Jupiter, past Neptune, and eventually past a boundary most people have never heard of. This is the solar wind, not a metaphor, not a poetic name for radiation. A physical stream of matter, mostly protons and electrons, peeling off the sun's outer atmosphere and accelerating outward through space at speeds that would cross the continental United States in about a tenth of a second. Every second, the Sun loses roughly 1 million tons of mass to this outflow. It has been doing this for nearly 5 billion years. The solar wind is not an occasional event or a byproduct of unusual activity. It is constant, relentless, and it fills the entire solar system in the way water fills a bathtub, pressed outward in every direction simultaneously, touching everything. When you picture the solar system, you probably picture the Sun at the center, the planets arranged in their orbits, and then empty space beyond. That picture is missing something. The solar wind does not stop at Neptune. It keeps going, past the Kuiper belt, past the scattered disk, out into the frozen reaches of space where the Sun is just a very bright star. As it travels, the wind thins out. It loses density, loses pressure, loses the energy that drove it outward, but it does not disappear. It keeps moving until something pushes back. And something does. The interstellar medium pushes back. The thin gas and dust that fills the space between star systems has its own pressure, its own momentum. Far enough from the Sun, the outward pressure of the solar wind and the inward pressure of the interstellar medium reach a balance point. That balance point has a name. It is called the heliopause, and it is the true edge of the Sun's reach. The region inside the heliopause, the entire bubble of space carved out by the solar wind, is called the heliosphere. Inside it, the Sun's wind dominates. Outside, it is interstellar space proper, the environment that has nothing to do with our star at all. The heliopause sits roughly 120 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun. So the heliopause is about 120 times farther from the Sun than we are. That sounds enormous. In interstellar terms, it is almost nothing. The nearest star system, Alpha Centauri, is about 270,000 astronomical units away. The heliosphere is a tiny soap bubble in an ocean. The solar wind is not uniform inside that bubble. The Sun produces different kinds of outflow depending on what is happening at its surface. Regions called coronal holes, darker, cooler patches where the Sun's magnetic field opens outward rather than looping back, release faster, less dense streams. Other regions associated with stronger magnetic activity produce slower but denser outflow. These different streams interact as they travel outward, creating a structured, variable environment. Speed, density, and magnetic field orientation all shift depending on which part of the Sun a given stream originated from. The solar wind you are sitting in right now is not the same solar wind that was here 6 months ago. Then there are the violent events. Coronal mass ejections are the largest. They happen when a region of the Sun's magnetic field becomes twisted and unstable, suddenly releasing an enormous bubble of magnetized plasma that can carry billions of tons of matter outward at millions of miles per hour. A large coronal mass ejection reaching Earth can compress the magnetosphere dramatically, inject energetic particles into the near-Earth environment, and for spacecraft or humans outside of a protective magnetic field, deliver a radiation dose in hours that would normally accumulate over months. These are not rare events. The Sun generates multiple coronal mass ejections per week during active periods of its roughly 11-year solar cycle. Most miss the Earth entirely. Some do not. When a large one hits, it is called a solar particle event, and for mission planners thinking about deep space travel, solar particle events are the acute version of a radiation problem that is chronic. For a spacecraft traveling toward Mars or beyond, there is no shelter. The sun's magnetic field threading through the solar wind provides some protection against galactic cosmic rays, high-energy particles coming from outside the solar system. But during a major solar particle event, that same field becomes a highway for solar energetic particles streaming outward, and the dose rates during the worst events would be dangerous to any unprotected crew within hours. Spacecraft electronics can be disrupted, navigation systems can be affected, communications can fail. The solar wind is the environment every deep space mission must account for, and the heliosphere it creates is both a domain and a kind of shield, imperfect, variable, but real. In 1977, NASA launched the Voyager 1 spacecraft. It flew past Jupiter, it flew past Saturn, it kept going. For 35 years it travelled outward, sending data back across distances that grew so large that the radio signal took hours to arrive. Scientists watched the measurements of the surrounding plasma change slowly over decades as Voyager moved deeper into the outer heliosphere. Then in 2012, something happened. The density of the solar wind plasma around the spacecraft dropped sharply. The magnetic field environment shifted, and the count of high-energy particles from outside the solar system jumped dramatically. Voyager had crossed the heliopause. It was in interstellar space, the first human-made object to get there. In 2012, when Voyager 1 crossed that boundary, its instruments registered a sharp jump in cosmic ray flux. The solar wind that had been holding those galactic particles at bay for 35 years was finally gone, and the full radiation environment of interstellar space was all around it. Earth's magnetic field is the reason this planet has an atmosphere, liquid water, and life, and almost nobody thinks about it on a daily basis. It is invisible. It makes no sound. You cannot feel it pressing against your skin. But remove it, and this planet becomes unrecognizable within a geologically short time. The solar wind, that million-mile-per-hour stream of charged particles described a moment ago, would begin stripping the upper atmosphere away, not all at once, gradually, over millions of years, the way a slow leak empties a tank. Mars is the clearest example we have of what that process produces. Mars once had a thicker atmosphere and liquid water on its surface. Its core cooled, its magnetic field died, and the solar wind spent the next few billion years dismantling whatever protection remained. Today, the Martian atmosphere is about 1% as dense as Earth's. Earth avoided that fate entirely because of what is happening roughly 3,000 kilometers beneath your feet right now. The outer core of this planet is liquid iron, churning under convection driven by heat escaping from deep inside. That churning, combined with Earth's rotation, generates an electric current on a planetary scale. That current produces a magnetic field. The field extends outward from Earth's surface in a roughly dipolar shape. Two poles, a network of field lines arcing between them, and a surrounding region of space where that field dominates. This region is the magnetosphere, and it extends roughly 60,000 kilometers toward the Sun and hundreds of thousands of kilometers in the opposite direction. Dragged into a long tail by the solar wind pressing against it from the sunward side. It is not a fixed, rigid shell. It breathes, it flexes, it responds to what the sun is doing at any given moment. On the side facing the sun, the solar wind compresses the magnetosphere inward. On the night side, the same wind stretches it out into a long magnetotail, that reaches roughly 600,000 kilometers behind the planet. This asymmetry is not a flaw. It is the shape the field takes under constant pressure from the solar wind. Most of the time, this interaction is stable. The solar wind flows around the magnetosphere the way water flows around a rock in a stream. Charged particles are deflected. Some are captured and spiral along field lines toward the poles, dumping their energy into the upper atmosphere and producing auroras. The rest are redirected away from Earth's surface without incident. Then something changes. The sun releases a coronal mass ejection, a billion-ton cloud of magnetized plasma flung outward at millions of kilometers per hour. It hits the magnetosphere, and the interaction stops being calm. The field compresses sharply on the sunward side. Particles that would normally be deflected punch through to lower altitudes. Auroras appear at latitudes that almost never see them. In strong events, the electromagnetic disturbances reach the ground. In 1989, a coronal mass ejection caused a geomagnetic storm powerful enough to collapse the entire power grid of Quebec within 92 seconds. 6 million people lost power. In the Carrington event of 1859, telegraph systems across North America and Europe failed spontaneously, some catching fire. That event, if it happened today, would cause damage estimated in the trillions of dollars. The magnetosphere was overwhelmed both times. It recovered, but the recovery took hours. For anyone standing on Earth's surface, even the worst of these events is mostly an inconvenience. The atmosphere itself adds another layer of protection below the magnetosphere. The layers of shielding here are deep. Now consider what it means to leave them. The International Space Station orbits at roughly 400 kilometers altitude. For most of its orbit, it sits inside the magnetosphere. Astronauts there receive measurable radiation, several times the dose of someone on the ground, but the magnetosphere is doing substantial work on their behalf. The Van Allen belts, two donut-shaped zones of trapped charged particles surrounding Earth, lie further out, between roughly 1,000 and 60,000 kilometers altitude. Flying through them requires care. The Apollo missions crossed the Van Allen belts on their way to the Moon, accumulating doses that were carefully tracked and kept as low as mission planning allowed by crossing quickly. The astronauts survived, but the exposure was real, and it was higher than anything experienced by crews on the ISS. Beyond the Moon, the picture changes again. There is no magnetosphere. There are no Van Allen belts. The solar wind moves through this space unimpeded. Earth's protection ends somewhere around 60,000 kilometers in the sunward direction. A crew heading toward Mars passes that boundary within hours of leaving cislunar space, and from that point forward, the only thing standing between them and the full particle flux of the solar wind is the wall of their spacecraft and whatever the sun's own magnetic field manages to deflect. The heliospheric magnetic field does provide some shielding against galactic cosmic rays, high-energy particles coming from outside the solar system. But that protection varies. During solar maximum, when the sun's magnetic field is stronger and more tangled, more galactic cosmic rays are deflected. During solar minimum, the flux increases. The effect is real but partial. It cannot be relied upon. It cannot be controlled. Plan a Mars mission to launch at the wrong point in the solar cycle, and your crew absorbs more galactic radiation than if you had timed it differently. Choose correctly and you reduce the dose, but you cannot eliminate it. The heliospheric magnetic field is not a shield in any robust sense. It is more like a partial fog that sometimes thickens and sometimes thins, and beyond it there is nothing. Once you cross the heliopause, the sun's magnetic field can no longer deflect galactic cosmic rays, and the radiation environment you are traveling through becomes something our species has no evolutionary preparation for whatsoever. The most dangerous thing in deep space cannot be seen, felt, tasted, or avoided. It passes through spacecraft walls. It passes through the human body. It has been crossing the galaxy for thousands of years before arriving at whatever it happens to hit next. Galactic cosmic rays are not a weather event you can shelter from. They are the permanent background condition of deep space, and the moment you leave the protection of Earth's magnetic field, they begin accumulating inside you whether you are paying attention or not. What they actually are is worth understanding precisely. Most galactic cosmic rays are protons, the nuclei of hydrogen atoms, moving at extraordinary speeds. A significant fraction are alpha particles, which are helium nuclei. Both of these are energetic and capable of causing biological damage. But the particles that concern radiation physicists most are a smaller subset known as HZE particles. HZE stands for high atomic number and high energy. These are the nuclei of heavier elements, iron, nickel, silicon, stripped entirely of their electrons and accelerated to velocities approaching the speed of light. They are produced by supernovae, by neutron star collisions, by the most energetic events the galaxy generates, and then they travel across interstellar space in essentially straight lines, losing very little energy over millions of years. When one of them hits you, it does not stop politely at the skin. To understand why HCE particles are categorically different from ordinary radiation, it helps to think about what conventional shielding actually does. X-rays and gamma rays are forms of electromagnetic radiation, photons. Lead stops them because the electrons in dense materials absorb and scatter those photons before they penetrate far. That is the principle behind the lead apron at the dentist. It works. With enough lead, you can stop almost any X-ray or gamma ray. HCE particles are not photons. They are physical matter moving at nearly the speed of light. When they enter a shielding material, they do not simply get absorbed. They collide with atomic nuclei and generate cascades of secondary particles, neutrons, protons, lighter fragments that spray outward in all directions. Add more shielding, and the secondary cascade gets worse. There is a real possibility that a certain thickness of conventional shielding material produces more damaging radiation inside it than the original particle would have delivered on its own. The engineering problem of protecting humans from HZE particles does not have a clean solution. You cannot simply build thicker walls. This is what makes deep space radiation fundamentally unlike anything we deal with on Earth's surface. Every medical imaging device, every nuclear power plant, every industrial radiation source comes with a shielding solution that works. Put enough material between the source and the person is protected. Galactic cosmic rays break that logic. The galaxy has been producing these particles for billions of years, and they arrive from every direction simultaneously. There is no orientation of a spacecraft that puts the shielding between the crew and the source, because the source is the entire galaxy. The numbers accumulate quickly once you start doing the arithmetic. In interplanetary space, beyond the magnetosphere and away from the heliosphere's partial protection, astronauts absorb roughly 1.84 millisieverts of radiation per day from galactic cosmic rays alone. That number may not mean anything on its own. A chest X-ray delivers about 0.1 millisieverts. A single day in interplanetary space delivers roughly 18 times that dose. A week delivers more than a typical CT scan of the abdomen. A month delivers a dose that would be considered a reportable occupational exposure for a radiation worker on Earth. These are not emergency doses. They are not the result of a solar flare or some anomalous event. They are simply the ordinary background rate of deep space, every day, all the time. A round trip to Mars, accounting for transit time in both directions and surface operations, runs to roughly 900 days. At 1.84 millisieverts per day in transit, and lower but still significant doses on the Martian surface, the total accumulated dose for such a mission runs well into territory that no current framework for occupational radiation exposure was designed to accommodate. NASA has career radiation limits for astronauts. Those limits are not arbitrary. They are derived from risk models for cancer and other radiation-related diseases, calibrated to the radiation environments of low Earth orbit, where the magnetosphere still provides partial protection. Deep space is not low Earth orbit. The exposure rates are different by a significant factor, and a Mars mission would require an astronaut to use up their career limit on a single flight, with years of career remaining. The biological consequences that concern NASA most have been organized into 4 categories. Carcinogenesis is the most familiar. The elevated lifetime risk of developing cancer from DNA damage accumulated over the mission. Cardiovascular disease through tissue degeneration is less obvious to the public, but well supported in the research, as ionizing radiation at these doses causes progressive damage to the cells lining blood vessels and the heart muscle itself. Acute radiation syndrome is the emergency scenario, the severe and immediate physiological collapse that follows a very large dose in a short period, the kind of dose a massive solar particle event could deliver to an unshielded crew in deep space. For any of those 3, there are at least established medical frameworks. Radiation oncology exists. Cardiovascular interventions exist. Emergency protocols for acute radiation syndrome exist. The 4th category is where certainty dissolves. Central nervous system damage from galactic cosmic ray exposure is the domain where the research is thinnest. The animal data is alarming, and the human data is almost entirely absent. HCE particles passing through brain tissue create long, narrow tracks of ionization damage that ordinary radiation cannot replicate. The structures they damage include the regions most responsible for memory, decision-making, and spatial reasoning. The consequences of that damage on a crew operating a spacecraft several 100 million kilometers from Earth are not fully understood by anyone alive. NASA's current career radiation limits for astronauts would be exceeded by a single Mars mission, and that calculation does not include what happens to the brain. In every radiation risk discussion about deep space travel, the central nervous system effects end up in a footnote, and they probably should not. The previous section laid out what galactic cosmic rays are and what they do to the body in broad terms. Cancer risk, cardiovascular damage, acute radiation syndromes. These are the numbers that fill the briefing documents and the mission planning spreadsheets. They are real and serious. But running underneath all of it, quieter and in many ways stranger, is a second problem. What these particles do specifically to the brain, not to tissue in general, not to DNA in some general cellular sense, to the organ that makes the crew capable of doing the mission at all. Here is what makes HCZ particles different from ordinary radiation. When a medical X-ray passes through you, It deposits energy in a scattered, relatively diffuse way. Cells are damaged, some are killed, the body repairs what it can. The damage is real, but it follows patterns medicine has studied for decades. HZE particles are not like this. A single iron nucleus traveling at a significant fraction of the speed of light does not scatter. It punches straight through tissue in a nearly straight line, ionizing everything along its path, leaving behind what researchers describe as a long ionization track, a streak of devastation through cells and DNA that conventional radiation simply cannot produce. The biological damage along that track is dense, clustered, and far harder for cells to repair accurately than the scattered damage from ordinary radiation. These are not the same kind of hits. They are categorically different. Now put that track through brain tissue, through neurons, through the specific structures that brain cells use to communicate with each other, form new connections, and generate new cells. The question stops being theoretical very quickly. The hippocampus is where the story gets specific and uncomfortable. This is the brain region most tightly linked to the formation of new memories, spatial navigation, and the kind of flexible learning that lets you take in new information and apply it to novel problems. It is also, for reasons that are not fully understood, one of the most vulnerable structures in the brain to a particular kind of insult, disruption of neurogenesis, the process by which new neurons are generated from stem cells in adult brain tissue. The hippocampus is one of the very few regions of the adult brain that continues producing new neurons throughout life. That process is sensitive. HZE exposure in animal studies conducted with particles calibrated to match the energy spectrum of deep space galactic cosmic rays disrupts it measurably. The results from those studies are not subtle. Rodents exposed to HZE equivalent doses showed long-term reductions in hippocampal neurogenesis. They showed changes in synaptic plasticity, the ability of neurons to strengthen or weaken their connections in response to activity, which is the cellular basis of learning and memory. And they showed deficits in spatial learning and memory tasks that persisted well after the exposure itself had ended. These were not temporary effects that faded as the animals recovered. The changes were durable. In some cases, they appeared to worsen over time. This is the kind of finding that should be at the front of every Mars mission discussion, not the back. Think about what you are actually asking a crew to do on a Mars mission. You are asking them to manage life support systems with thousands of individual parameters, to perform surgical procedures on each other if required, to navigate orbital mechanics and landing sequences under time pressure, to diagnose equipment failures and improvise repairs with whatever is on hand, to remember complex emergency procedures under stress, to make good decisions when they are exhausted and far from any help. Every single one of those tasks depends on a brain that is functioning well. Specifically, many of them depend on the hippocampus functioning well, and the hippocampus would be absorbing HZE tracks for the entire duration of the transit, both ways. The most alarming part of the timing is this: the highest demand moments of a Mars mission, the orbital insertion, the landing, the surface operations, the launch back off Mars, the Earth return, all of these happen after the crew has been exposed to the full radiation environment for months or years. A crew arriving at Mars after 7 months of deep space transit has been absorbing galactic cosmic rays for 7 months. Whatever cognitive effects have accumulated are already there. They brought them with them. Now, the honest qualification. Almost all of the hard data here comes from animal studies. rodents, some primate work, carefully controlled laboratory exposures that simulate the deep space environment as accurately as current accelerator technology allows. Human data is thin. No human being has ever spent the full duration of a Mars mission in the unshielded deep space radiation environment. ISS astronauts accumulate radiation exposure, but the ISS sits inside Earth's magnetosphere for much of its orbit, and the radiation environment there is meaningfully different from deep space transit. The ISS data is useful, it is not sufficient. Modeling fills in some of the gaps. Researchers have built computational estimates of what expected dose rates and particle spectra would do to human brain tissue over a 900-day round trip. The models are sophisticated. They are also models. They can only predict based on what the animal data and the physics suggest. The brain is not a simple system. Long-term neurological effects in humans may follow different timelines, different severity curves, different recovery patterns than what the animal work implies. They could be better, they could be worse. Agencies planning crewed Mars missions within the next 15 to 20 years are working with this uncertainty baked into their risk frameworks. They are setting acceptable exposure limits, developing pharmacological countermeasures, studying shielding strategies. All of that work is proceeding, but the gap between the models and the actual human answer is not something engineering alone can close. The honest scientific answer to what a 3-year Mars mission does to the human brain is that we do not know, and we will not know until someone actually does it. The first thing that happens when you take a human being out of gravity is that their inner ear lies to them. The vestibular system, the cluster of fluid-filled canals and tiny calcium crystals deep in your skull, has spent your entire life doing one job: detecting how your body is oriented against gravity's pull. Remove gravity, and those signals stop making sense. The canals still register movement, the crystals still shift, but the reference point they have been calibrated against for decades is simply gone, and the brain, receiving contradictory information from the eyes and the ears and the body, does what any overwhelmed system does. It panics. The result is space adaptation syndrome, disorientation, nausea, vomiting, a persistent sense that up and down are suggestions rather than facts. Roughly 2/3 of astronauts experience it to some degree in the first hours after reaching orbit. Most recover within a few days. By the end of the first week, the brain has generally updated its model of the world, and the worst of it passes. That resolution, though, is almost the only good news in what follows. Once the acute phase settles, the slow damage begins. It is quiet, cumulative, and in some ways more alarming than the disorientation, because it does not announce itself. The first major shift involves fluid. On Earth, gravity pulls blood and fluid toward the lower body. Legs swell slightly by the end of a long day. The heart pumps against that gradient constantly. In microgravity, that gradient disappears. Fluid redistributes evenly, which means it moves toward the head. Astronauts describe their faces feeling puffy, their nasal passages congesting, a persistent pressure behind their eyes. The body interprets this redistribution as fluid overload. It responds logically by reducing total fluid volume. Plasma levels drop, red blood cell production falls. The heart, suddenly working against a much easier load, begins to shrink because it no longer needs the same mass of muscle. Immune cell counts decrease. The body is essentially dismantling systems it has decided are now over-engineered for the environment it finds itself in. This is adaptation working perfectly. It is also catastrophic from the standpoint of anyone who plans to return to a gravity environment. Bone loss is where the numbers become genuinely alarming. Bone is not static tissue. It is constantly being broken down and rebuilt, and the signal that drives rebuilding is mechanical load. Stress the bone, and it responds by reinforcing itself. Remove the stress, and the rebuilding signal weakens while breakdown continues. In microgravity, the bones of the lower skeleton, the femur, the tibia, the lumbar vertebrae, lose roughly 1 to 2% of their density every month. A 6-month mission on the International Space Station can produce bone loss equivalent to what a person on Earth might accumulate over 1 to 2 decades of aging. The loss is not uniform across the body. The upper skeleton, which still bears some load from movement, fares better. The bones that evolved to hold a body upright against gravity bear the full cost. Some studies suggest that with aggressive exercise countermeasures, the rate can be slowed but not stopped. Recovery after landing takes months. For some astronauts, bone density never fully returns to pre-flight levels. 6 months does this. A 3-year mission is a different calculation entirely, and nobody has run that experiment on a human being yet. Muscle follows the same pattern, and for the same reason. Skeletal muscle in the legs and lower back exists largely to fight gravity. Stand up, walk across a room, climb a step. All of that work maintains muscle mass through continuous low-level loading. In microgravity, the legs are largely passengers. Astronauts float from handhold to handhold. The legs push off walls, but they do not bear weight. The result is rapid atrophy, particularly in the postural muscles along the spine and in the quadriceps. Even with 2 hours of daily exercise on the ISS, a regimen specifically designed to slow this process, significant loss occurs. Returning astronauts often cannot walk unassisted immediately after landing. Some have to be carried from the capsule. The muscles that move them exist. The endurance and the coordination trained against a gravitational load are not there in the same form. Then there is the spine. Gravity compresses it constantly. Every intervertebral disc is slightly squeezed by the weight of the body above it. Remove that compression and the discs expand. Astronauts gain an inch or two in height within days of reaching orbit. This sounds benign. It is not particularly benign in practice. The expansion is uneven, and the soft tissues surrounding the spine, muscles, and ligaments calibrated for a compressed configuration suddenly find themselves under different tension. Back pain is common and often severe in the first weeks of a mission. Some astronauts report that the height gain reverses faster than expected upon return, compressing structures that had adjusted to the expanded state, producing a second round of discomfort. What recovery looks like after a standard 6-month ISS mission involves months of physiotherapy and careful reintroduction of gravitational loading. Astronauts relearn how to walk with a coordination that feels foreign. Balance systems that spent months ignoring gravity have to be recalibrated. Cardiovascular fitness has to be rebuilt. The process takes at minimum several months, and it is managed by a full rehabilitation infrastructure that begins immediately upon landing. That infrastructure exists because returning to Earth's gravity after 6 months is already medically significant. Now consider what extending that timeline to 3 years implies. The bone loss projections alone push into territory with no clear recovery pathway. The muscle atrophy, the cardiovascular deconditioning, the immune suppression, the spinal changes, All of it compounds over a timeline that no human has experienced and no rehabilitation program has been designed to address. A crew that has spent 3 years in microgravity or on Mars at 38% of Earth's gravity and then has to land on Earth and walk off a spacecraft in front of cameras may not be able to walk at all. One of the stranger things that happens to astronauts on long missions is that they gradually lose the ability to focus their eyes. Not from fatigue, not from the stress of living in a machine hurtling through vacuum. The cause is something quieter and more fundamental. The same fluid shift toward the head that was already reshaping the heart and suppressing the immune system. That shift does not stop at the neck, it keeps going. In a normal gravity environment, cerebrospinal fluid is partially pulled downward by the constant pull of the Earth. It distributes unevenly, held in place by the same force that holds everything else in place. Remove gravity, and that changes. In microgravity, cerebrospinal fluid spreads more evenly throughout the skull and spinal canal. The total volume does not change dramatically, but the distribution does. And what that redistribution does to pressure inside the skull is significant. Intracranial pressure rises. Slowly, steadily, without the astronaut necessarily feeling anything alarming. The pressure builds and presses outward against whatever it meets. What it meets, among other things, is the back of the eye. The optic disc, the point where the optic nerve connects to the retina, begins to change shape under that sustained pressure. The eyeball itself flattens slightly at the back. Layers of the chorioretina, the tissue behind the retina, begin to develop folds. None of this is supposed to happen. All of it does happen in a significant fraction of astronauts who spend months aboard the International Space Station. Some return needing reading glasses for the first time in their lives. Some experience changes that do not fully reverse after landing. The technical name for this cluster of findings is Spaceflight-Associated Neuroocular Syndrome, or SANS, and it did not have a name until fairly recently because no one had been looking for it carefully enough or long enough to recognize the pattern. When SANS was first systematically studied, the numbers were striking. Roughly 40% of astronauts returning from long-duration ISS missions showed some measurable structural change to the eye. Some changes were minor, some were not. What no one could say with confidence was how much worse the problem would get on a mission 3 times as long, traveling far beyond low Earth orbit, where no return window exists, no surgeon is available, and the fluid pressure keeps doing what fluid pressure does. On a Mars mission, this is not an inconvenience. This is a mission-critical problem. The tasks that require functional vision on a crewed spacecraft are not optional. Reading displays, monitoring instruments, performing mechanical repairs, administering medical care to other crew members, all of it depends on eyes that work correctly. A crew member with progressively worsening nearsightedness, optic disc swelling, and chorioretinal folds, halfway to Mars with no ophthalmologist and no surgical option, is a crew member whose capability to perform those tasks is degrading in real time. There is currently no confirmed countermeasure that reliably prevents SANS. Lower body negative pressure devices which pull fluid back toward the legs artificially are being studied. Nothing has been proven at the scale and duration a Mars mission would require. The eyes are not the only sensory system absorbing unexpected damage. Hearing is another. The interior of a spacecraft is not quiet. It has never been quiet. Pumps cycle, fans run, mechanical systems generate constant broadband noise during launch, during transit, and at every point in between. Prolonged exposure to that acoustic environment, measured over months, constitutes a genuine hearing loss risk. Astronauts returning from long ISS stays have shown measurable shifts in auditory thresholds. The effect is less dramatic than the vision problem, but it accumulates the same way, quietly, gradually, without any single moment of obvious damage. Then there is the issue that almost nobody mentions in the serious literature, but that says something almost elegant about what the body actually is: the soles of the feet. On Earth, your feet bear your weight. The skin on the soles thickens in response, building calluses where pressure is greatest. It is a simple adaptation. In microgravity, your feet never touch the floor. They are not used for standing. They are used for hooking under handrails and footholds to stabilize position while working. Within weeks, the calluses on the soles begin to soften and disappear because there is no pressure signal telling the body to maintain them. And within the same time frame, the skin on the tops of the feet begins to thicken where the footholds press. The body reads the actual mechanical environment it inhabits, with no interest in what that environment is supposed to be, and adjusts accordingly. It does not know it is on a spacecraft. It does not know anything. It measures pressure, force, and demand, and it responds. That response is happening simultaneously across every system. The heart shrinks, the bones thin, the eyes deform, the ear loses sensitivity, the feet invert their calluses. Each adaptation is the body doing exactly what bodies do, optimizing for the conditions it actually detects, not the conditions that would be necessary for the mission to succeed, not the conditions the crew will need to function in when they return, just the conditions it finds itself in right now. The body has no loyalty to what worked on Earth. It adapts to whatever environment it actually finds itself in, which is why astronauts return from the space station with soft feet and calluses on the wrong side. The question of what happens to an unprotected human body in deep space comes up often, and almost every popular answer gets something wrong. Movies have been running with the same set of images for decades. Bodies explode, skin freezes in seconds, eyes go wide, and then the person is gone. None of that is accurate, and the real sequence of events is stranger and more specific than Hollywood has ever bothered to render. Start with the lungs, because the lungs are the first problem. The moment you are exposed to vacuum, the pressure differential between your body and the surrounding environment becomes roughly 14 pounds per square inch in favor of your interior. Gas wants to go where there is less of it. If you exhale first, the air leaves cleanly and nothing ruptures. If you try to hold your breath, that same pressure tears your lungs apart within seconds. This is not a slow process. The tissue damage is immediate and severe. Every diver who has ever surfaced too fast understands a gentler version of this physics. In true vacuum, there is no gentler version. Immediately after that, you notice your eyes. The thin film of moisture on the surface of the cornea evaporates almost at once. There is no air pressure holding it in place, no atmosphere trapping it against the surface. The same thing happens to the inside of your mouth. What people in the handful of documented near vacuum exposure incidents have described is a stinging, cold sensation, a sudden dryness so complete it is almost painful. Your saliva begins to bubble, not because the temperature has spiked, but because the boiling point of water is not fixed. It depends on pressure. At sea level, water boils at 100 degrees Celsius. Drop the pressure far enough and water boils at 37 degrees Celsius. That is body temperature. The fluid on the surface of your tongue and lips reaches its new boiling point instantly. The same process is working inside your body tissues, and this is where movies take the physics and run in the wrong direction. Water in your soft tissues begins to vaporize. The result is swelling, visible and significant swelling, as gas forms inside the tissue and pushes outward. Your body does not explode. The skin is elastic enough to contain the expansion, and the process is not instantaneous. What you would look like is bloated, noticeably larger than normal, a person-shaped object that has been inflated slightly beyond its intended dimensions. Dramatic, yes. An explosion? No. The blood does not boil the way a pot of water boils on a stove. The cardiovascular system is a closed pressurized circuit. The heart and vessels maintain enough internal pressure that the blood stays liquid. What you would see is a sharp drop in blood pressure as the body's fluid dynamics respond to the vacuum. But full-scale vaporization of the circulatory system is not what happens. The reality is more mundane and more final. The blood stops carrying oxygen. The oxygen that was already in circulation runs out quickly, and the brain, which is extraordinarily intolerant of interruption, starts shutting down. Consciousness holds for roughly 10 to 15 seconds. This has been estimated from what we know about hypoxic blackout, and from at least one documented case of a man who was accidentally exposed to near-vacuum conditions in a NASA altitude chamber in 1965. He reported feeling the saliva boiling on his tongue before losing consciousness. He survived because the pressure was restored quickly. In open deep space, no one is restoring the pressure. By 15 seconds, you are unconscious. By 4 to 5 minutes, the brain damage is irreversible. Death follows. Now, the cold. The temperature of deep space, set by the cosmic microwave background, is about 2.7 Kelvin. That number sounds instantly lethal. It is not the mechanism that kills you. In vacuum, there is no medium to conduct heat away from your body. Conductive cooling requires contact with something colder. Convective cooling requires a fluid. In vacuum, there is neither. The only way heat leaves you is through radiation, and radiative cooling at human body temperatures is extremely slow. You would be losing heat at a rate measured in watts, not the rapid drain of falling into ice water. You would be dead from oxygen deprivation many minutes before the cold dropped your core temperature to anything dangerous. The freezing is real, but it is an afterthought in terms of the timeline. You would not explode, you would not freeze in seconds, and your blood would not boil like water in a pot. You would swell slightly, lose consciousness in about 15 seconds, and be dead within a few minutes, which is less dramatic but more accurate. One of the more disorienting predictions of general relativity is that time does not pass at the same rate everywhere in the universe. Not approximately the same rate, not close enough to ignore. Actually, measurably, precisely different rates depending on where you are standing and how much mass is nearby. Einstein's general relativity describes gravity not as a force in the traditional sense, but as a curvature in the fabric of space-time itself. Massive objects bend that fabric, and time, embedded in that fabric, bends with it. The stronger the gravitational field around you, the slower time runs. This is not a philosophical abstraction. It has been confirmed in laboratories on Earth using atomic clocks accurate enough to detect the effect across a difference in altitude of a few feet. A clock on the ground floor of a building runs measurably slower than one on the top floor. The gravitational field at ground level is infinitesimally stronger, and time responds. The effect at human scales is so small it barely registers. but scale it up to the densities and masses that exist in deep space, and the numbers become genuinely strange. GPS satellites offer the cleanest everyday example. They orbit at an altitude where gravity is slightly weaker than at Earth's surface. Time on a GPS satellite runs faster than time on the ground by about 38 microseconds per day. That sounds trivial. For a navigation system that calculates positions by timing light pulses with nanosecond precision, 38 microseconds of daily drift would compound into kilometers of positional error within hours. Every GPS satellite carries a clock correction built into its design specifically to account for this. Gravitational time dilation is not a theoretical curiosity in this case. It is an engineering specification. Now take that effect and move it to environments that make Earth's gravity look like a gentle suggestion. A neutron star packs more mass than the Sun into a sphere roughly 12 miles across. The gravitational field at its surface is so extreme that a clock sitting there would run approximately 30% slower than one far away. 30%. An observer standing on the surface of a neutron star, if they could survive for even a second, would be aging at 70% the rate of someone watching from a safe distance. An astronaut who somehow orbited close enough to a neutron star to feel that gradient strongly, and spent what felt to them like a year there, would return to find that more years had passed for everyone else. The calendar would have moved further than their body had. This is where people tend to assume science fiction is taking over. It is not. The equations that predict this effect are the same equations that correct your phone's GPS every second of the day. The physics does not change, only the magnitude changes. Near a neutron star, the magnitude becomes extreme. Near a stellar mass black hole at the event horizon, it approaches something harder to hold in the mind. From the perspective of a distant observer, a clock falling toward the event horizon appears to slow down and stop. It never crosses. It freezes at the edge, red-shifted into invisibility. From the perspective of the infalling clock, it crosses in finite time and feels nothing unusual at the moment of crossing. Two observers, two entirely valid descriptions, one physical event. This is what general relativity does. It replaces the comfortable idea of a single universal clock with something far less forgiving. Deep space is not uniform in any of this. The fabric of space-time is being pulled and curved by every massive object in the universe simultaneously. The degree of that curvature varies enormously depending on location. In the deep voids between galaxy clusters, where matter density drops to almost nothing, and the nearest significant mass is hundreds of millions of light-years away, space-time is about as flat as it gets. Time there runs at nearly its maximum possible rate. There is nothing nearby heavy enough to slow it. A hypothetical clock drifting through the center of the Boötes Void would tick faster than almost any clock in a denser region of the universe. Move that clock toward a galaxy cluster and the situation changes. Galaxy clusters contain hundreds to thousands of individual galaxies, vast clouds of hot gas, and enormous halos of dark matter. The combined mass is staggering. Space-time near a massive cluster is detectably curved, not just for clocks but for light itself. Light has no mass, but it follows the geometry of space-time, and where that geometry curves, light curves with it. A beam of light travelling past a massive galaxy cluster does not travel in a straight line. It bends. The cluster acts as a lens. Astronomers first predicted this effect from Einstein's equations and confirmed it during the 1919 solar eclipse, when stars near the Sun's edge appeared shifted from their true positions by almost exactly the amount the equations predicted. That was a relatively mild curvature. At the scale of a galaxy cluster, the lensing is dramatic enough to see in ordinary telescope images. Distant galaxies behind the cluster appear stretched into arcs, smeared across the sky in curved streaks, occasionally split into multiple images of the same object appearing in different positions around the cluster. This is the same galaxy, the same light, arriving at slightly different angles because the curved geometry of space bent different portions of the beam along different paths. The practical consequence is that some of the most distant objects ever observed were discovered using clusters as amplifiers. The cluster magnifies and brightens sources that would otherwise be too faint to detect. Scientists choose their targets carefully, positioning telescopes to look through known clusters at the most promising patches of sky behind them. The universe's own geometry becomes an instrument. The curvature of space near a massive galaxy cluster is so pronounced that astronomers routinely use those clusters as natural telescopes, letting the bent geometry of space-time magnify objects billions of light-years behind them. The most extreme object in the universe that is not a black hole is about 12 miles across, weighs more than the Sun, and spins hundreds of times per second. That sentence does not pass easily. 12 miles is the length of a city, Manhattan roughly. The Sun contains 99% of all the mass in the solar system. Hold both of those facts at the same time, and something in the mind resists them. Yet this is not a theoretical construct or a prediction waiting to be confirmed. Neutron stars exist throughout the galaxy right now, and the physics that produces them is among the most thoroughly tested in all of astrophysics. To understand what a neutron star is, you have to understand what makes one. When a star somewhere between roughly 8 and 20 times the mass of our Sun reaches the end of its life, the iron core at its center stops generating energy through fusion. Iron cannot fuse into anything that releases power. The moment that core goes inert, gravity wins. The core collapses in less than a second, falling inward at around 70,000 kilometers per second. At those pressures and densities, something remarkable happens. Electrons and protons are forced together. They merge. What remains is a sphere of neutrons packed so tightly that the normal rules of matter simply stop applying. The result is a neutron star, roughly 10 to 12 miles across, more mass than the Sun compressed into a ball smaller than most cities. The density involved is almost beyond communication. A single teaspoon of neutron star material would weigh roughly 1 trillion kilograms on Earth. Not 1 million, not 1 billion, 1 trillion. That is the mass of a mountain concentrated into a volume you could hold in your hand, if your hand could survive the attempt, which it absolutely could not. The surface gravity of a neutron star is about 200 billion times stronger than what holds you to Earth right now. A marshmallow dropped from a modest height onto the surface of a neutron star would hit with roughly the energy of a nuclear weapon. Not because the marshmallow is special, because at that gravitational field strength, anything falling even a short distance arrives with catastrophic kinetic energy. The surface temperature hovers around 1,000,000 degrees Celsius. The star radiates in X-rays. Even the cooling process, as the neutron star ages over thousands of years, is a slow bleed of thermal energy that astronomers track with space-based observatories because no ground-based telescope can see it. The combination of these conditions means that neutron stars represent a natural laboratory for physics that cannot be replicated anywhere else in the universe. No human facility could recreate what happens on a neutron star's surface and may never be able to. The physics that governs these objects operates at the absolute frontier of what we understand about matter itself. It is not merely a theoretical concern, it is a real place, orbiting within our galaxy, where the fundamental rules of reality are pushed to their limits. Astronomers have identified hundreds of neutron stars close enough to study with modern telescopes. These distant objects continue to reveal new insights about the extreme behavior of matter under conditions that exist nowhere else. Then there is the magnetic field. The magnetic field of a neutron star is, depending on the specific object, somewhere between 1 billion and 10 trillion times stronger than Earth's. The strongest electromagnets humans have ever built, the most powerful laboratory magnets ever constructed, are trivial by comparison. At a distance of roughly 1,000 miles from the surface of a neutron star, that magnetic field would be strong enough to tear the iron atoms directly out of the hemoglobin in your blood. Not damage you, not cause radiation sickness. Structurally dismantle the molecules your blood depends on, from the outside in, while you are still 1,000 miles away from the surface itself. The neutron star would not need to touch you. Some neutron stars spin, not slowly, the way the Earth turns once per day, but fast, hundreds of full rotations per second. These are pulsars, and they produce something that baffled the first person who detected one. As a pulsar spins, its powerful magnetic field generates 2 narrow beams of radio waves that sweep through space like lighthouse beams. From Earth, if one of those beams happens to point our way during each rotation, we detect a pulse, then another, arriving with such precise regularity that the timing rivals atomic clocks. In 1967, a graduate student named Jocelyn Bell Burnell was working with a radio telescope in Cambridge and found a signal pulsing every 1.33 seconds without variation. She and her supervisor initially labeled it LGM1. LGM stood for Little Green Men. The signal was so regular, so artificial seeming, that an extraterrestrial origin was seriously considered. It was not an alien transmission. It was a pulsar, the collapsed remnant of a dead star, broadcasting its rotation to the universe with metronomic precision. The timing of some pulsars is so stable that they have been proposed as navigation references for deep space missions, the way GPS uses satellites. Then there are magnetars. These are neutron stars whose magnetic fields are, somehow, even more extreme than the standard already incomprehensible baseline. Magnetars have fields so intense that they periodically crack. The crust of a neutron star is not rock. It is a crystalline lattice of neutrons and exotic nuclear matter, and it is under such magnetic and gravitational stress that it periodically fractures, releasing enormous bursts of gamma rays. These are called starquakes, and the energy they release dwarfs anything a normal star could produce in a comparable time frame. In 2004, a magnetar 50,000 light-years away released a burst of energy that lasted about 0.2 of a second and was more powerful than anything the sun could produce in 100,000 years, and we detected it easily from Earth, which should tell you something about the scale. A black hole is not a thing so much as a boundary, a region of space where the geometry of space-time has curved so severely that nothing, including light, has a path that leads outward. That distinction matters. Most people picture a black hole as an object, something sitting in space like a dark planet or a drain in a bathtub. It is not. There is no surface to hit. There is no wall. There is a boundary called the event horizon, past which the mathematics of general relativity says escape is not merely difficult, but geometrically impossible. Every path through space-time, including the path light takes, curves inward. The direction called outward simply stops existing past that line. And that line is invisible. You would cross it without feeling a thing, without any physical marker telling you it had happened. The only way to know you had passed the event horizon of a large enough black hole is that you could never again send a signal home. Where do black holes come from? The same place neutron stars come from. Massive stellar cores collapsing at the end of their lives. The difference is mass. When the collapsing core exceeds roughly 2.5 solar masses, neutron degeneracy pressure, the quantum pressure that holds a neutron star together, cannot stop the collapse. The matter keeps falling inward. General relativity predicts it falls all the way to a point of infinite density called a singularity. The collapse takes a fraction of a second. What was once the core of a star becomes a region of space-time so warped that nothing escapes it. There are three broad categories: stellar mass black holes, ranging from a few to roughly 100 solar masses, form from collapsing stars and are scattered throughout galaxies by the hundreds of millions. Then there are intermediate mass black holes, somewhere between a few hundred and a few 100,000 solar masses. These are the least understood category. Astronomers know they should exist, have found candidates, but the formation pathways are still debated. At the top end are supermassive black holes, the giants lurking at the centers of virtually every large galaxy. The one at the center of our own Milky Way, called Sagittarius A, contains about 4 million solar masses. The one at the center of the galaxy M87, which astronomers imaged directly in 2019, contains 6.5 billion solar masses. Numbers like these stop meaning anything to human intuition almost immediately. What would crossing an event horizon actually feel like? The answer depends entirely on which black hole you are crossing into. For a stellar mass black hole, you would not survive to reach the event horizon at all. The tidal forces, the difference in gravitational pull between your head and your feet, would become catastrophic while you were still thousands of kilometers away from the horizon. The technical term astronomers use is spaghettification, and the word is not an exaggeration. Your body would be stretched lengthwise and compressed sideways until you were drawn into a thin stream of particles. You would never see the inside. The tidal gradient kills you first. For a supermassive black hole, the situation is strangely different. The event horizon of a black hole, the mass of M87's central monster, is so large, roughly 20 billion kilometers across, that the tidal forces at the horizon itself are remarkably gentle. You could cross it without feeling anything unusual. The realization that you had passed into a region of no return would come not from sensation, but from calculation. And then, falling inward, the tidal forces would eventually grow. You would not escape that fate, but the horizon itself would offer no warning. Once inside, the singularity waits. General relativity describes it as a point of infinite density. But most physicists believe that prediction is a sign that the theory has reached the edge of its own validity, not a literal description of what exists. Infinite density is a mathematical answer that tells you the equations have broken down, the way a calculator gives you an error when you divide by 0. The real answer at the singularity is unknown because the real answer requires a theory of quantum gravity. a framework that merges quantum mechanics with general relativity. We do not have one. Decades of effort by some of the most capable physicists alive have not produced a complete, tested theory of quantum gravity. String theory offers candidates. Loop quantum gravity offers candidates. None has been confirmed. The singularity at the heart of a black hole is where our ignorance is most complete, and it is a kind of boundary of a different sort, not just the edge of a region of space, but the edge of what our current physics can say. The universe is full of information. Light carries it. Particles carry it. Every event that has ever happened has in principle left some trace that could, with enough capability, be read. Black holes appear to violate this. Whatever falls past the event horizon is gone. No signal, no particle, no information escapes. This bothered physicists enormously, and it led Stephen Hawking to one of his most consequential predictions. Quantum mechanics says the vacuum is not truly empty. At every point in space, pairs of particles and antiparticles flicker into existence and annihilate each other almost immediately. Near the event horizon of a black hole, Hawking argued, one particle from such a pair can fall inward while the other escapes. To a distant observer, the black hole appears to radiate. This is Hawking radiation. The energy for it comes from the black hole's own mass, which means the black hole very slowly loses mass and, over an almost incomprehensibly long time, evaporates entirely. For a stellar mass black hole, the timescale involved is roughly 10 to the power of 67 years. The current age of the universe is about 1.4 times 10 to the power of 10 years. A stellar mass black hole radiating away via Hawking radiation will outlast the universe's current age by a factor that cannot be written in ordinary language without scientific notation. Supermassive black holes take even longer. This evaporation has never been observed. The signal is too faint, the timescale too vast. It remains a theoretical prediction with no experimental confirmation. Hawking radiation also reopened the information question in a different form. If the black hole evaporates, does the information that fell in come out encoded in the radiation, or is it destroyed? This is the black hole information paradox, and it remains unresolved. Physicists argue about it actively. The stakes are not minor. If information is truly destroyed inside a black hole, it would require revising foundational principles of quantum mechanics. The inside of a black hole is the one place in the universe where the physics we have spent centuries building simply stops working, and whatever replaces it is a theory we have not written yet. The death of a massive star is the most energetic event in the observable universe that is not the Big Bang itself. To understand what that actually means, you need numbers. Not vague, impressive-sounding numbers, but specific ones, because the vague version does not do it justice. When a massive star, something between 8 and 100 times the mass of our Sun, reaches the end of its life, it has spent millions of years fusing lighter elements into heavier ones. Hydrogen into helium, helium into carbon, carbon into oxygen, neon, silicon, and eventually iron. Iron is where everything stops. Iron is the ash at the bottom of the furnace. Fusing iron does not release energy, it consumes it. The moment a star builds an iron core large enough, fusion stops generating the outward pressure that has been holding the star up against its own gravity for its entire existence. Gravity wins, immediately. What happens next takes less than 1 second. The iron core, roughly the size of Earth, collapses inward. Not slowly, not gradually, the core falls inward at approximately 70,000 kilometers per second, a quarter of the speed of light, and it does this in the time it takes you to blink. The core compresses until the neutrons themselves resist further compression, what physicists call neutron degeneracy pressure, and the collapse suddenly stops. The core bounces. That bounce sends a shock wave outward through the infalling layers of the star at a speed that tears the entire outer structure apart. The star does not burn out. It does not gently fade. It explodes from the inside out. The total energy released in the collapse is staggering. Roughly 300 times what our sun will radiate across its entire 10 billion year lifetime. All of that energy is released in seconds. But here is the part that stops people. 99% of it never makes it into the visible explosion at all. Almost all of that energy goes into neutrinos, nearly massless particles that interact with matter so weakly they pass through the entire mass of the dying star in seconds, escaping into space as though the star were not even there. They pass through Earth the same way. Billions of neutrinos from the last nearby supernova pass through your body without disturbing a single atom. The visible explosion, the thing that can outshine an entire galaxy, is just the leftover 1%. Think about that for a moment. The greatest light show in the universe is the scraps. When that 1% reaches the surface, the brightness that erupts is almost impossible to situate in human experience. A supernova at its peak can radiate more light than every star in a galaxy of 100 billion suns combined. In 1054, Chinese astronomers recorded a new star appearing in the sky, so bright it remained visible in full daylight for 23 days and continued glowing at night for almost 2 years. That was a supernova, roughly 6,500 light-years away. If a star at that distance exploded today, it would cast shadows on the ground at noon. If Betelgeuse, 650 light-years away, went off, the brightness would be difficult to look at directly. After the explosion fades, 2 things remain. The first is the remnant shell, a rapidly expanding bubble of gas and dust, superheated, glowing, and enriched with every heavy element the star spent its life forging, plus a collection of even heavier elements produced during the explosion itself. This expanding shell is called a supernova remnant, and it drifts outward through the surrounding interstellar medium for thousands of years, eventually dispersing. At the center of that shell sits the second remnant, the collapsed core. Depending on the mass of the original star, this becomes either a neutron star or a black hole. The star is gone. These 2 objects are what it leaves behind. The heavy elements carried in that expanding shell matter enormously. Every element heavier than iron in the periodic table, gold, silver, platinum, uranium, the iodine in your thyroid, the zinc in your cells, was forged in a supernova. The silicon in computer chips came from supernovae. The calcium in teeth came from supernovae. The distribution of these elements through galaxies is almost entirely the work of stellar explosions, seeding the interstellar medium over billions of years. Generation after generation of dying stars enriching the gas clouds that become the next generation of stars and planets. This process is not a poetic metaphor. It is the actual mechanism by which complex chemistry becomes possible in the universe at all. Without supernovae, the periodic table stops at iron, and everything built from heavier elements, which includes most of what we consider interesting, does not exist. For most of astronomical history, supernovae were observed only in their aftermath. A flash of light, a brightening sky, and then the slow fade as astronomers tried to reconstruct what had happened from the debris. In 2022, something different occurred. A supernova designated SN2022 Li appeared in galaxy NGC 157. As researchers studied the light coming from the remnant, they found a periodic signal, a regular brightening and dimming cycling roughly every 12 days. The pattern had a specific signature. The star that exploded had a companion, a second star orbiting closely, and that companion had survived the blast. The newly formed compact object at the center of the remnant, a neutron star or a black hole, the question was not yet settled, was orbiting the companion and stripping hydrogen gas from its outer atmosphere once every 12 days. The periodic accretion released energy that showed up as regular pulses in the brightness data. Nobody had watched this process begin in real time before. The compact object was, within the span of a human observation campaign, already doing what neutron stars and black holes do, pulling matter from whatever they can reach, heating it, and radiating the energy outward. In 2022, astronomers caught a supernova remnant in real time, stripping gas from its surviving companion star. The first direct observation of a newly formed neutron star or black hole, immediately behaving like the compact object it had just become. Everything visible in the universe, every star, planet, nebula, and galaxy, accounts for about 5% of everything that exists. The other 95% is something else entirely, something that does not glow, does not reflect, does not absorb light, and cannot be seen by any telescope ever built. It is detected only by the gravitational fingerprints it leaves on the things we can see. That number, 5%, is worth sitting with. Everything that has ever been observed, catalogued, named, or photographed in the history of astronomy represents a thin residue sitting on top of a universe that is almost entirely hidden from us. The first serious signal that something was wrong came from the way galaxies spin. When you look at our solar system, the pattern is straightforward. Mercury moves fast. The outer planets move slowly. Neptune at the far edge crawls along at roughly 5 kilometers per second while Mercury races at nearly 48. This is what gravity demands. The closer you are to the mass at the center, the faster you must travel to maintain your orbit. The same logic should apply to galaxies. Stars near the galactic center should orbit quickly. Stars at the outer edge should orbit much more slowly. When Vera Rubin began carefully measuring the rotation of galaxies in the 1970s, she expected to see exactly that. She did not. The outer stars were moving just as fast as the inner ones, sometimes faster. The rotation curves, instead of falling off as distance from the center increased, stayed stubbornly flat. This was not a small discrepancy. It was not measurement error. Rubin checked her data. Other astronomers checked it behind her. The result was the same for galaxy after galaxy after galaxy. Something was holding those outer stars in their orbits. Something with mass. Something that was not there when you looked. The only explanation that made sense was a vast halo of invisible mass surrounding each galaxy, extending far beyond the visible disk, contributing far more gravitational pull than all the stars and gas and dust combined. Rubin called it dark matter. The name stuck, though it tells you almost nothing about what it actually is. The same problem appears at larger scales. Galaxy clusters, the enormous structures where hundreds or thousands of galaxies are bound together by gravity, contain far more gravitational mass than their visible contents can explain. Astronomers can measure the mass of a cluster two ways: by counting the light coming from it and estimating how many stars that implies, and by measuring how fast the galaxies inside are moving and working backward to calculate what mass must be holding them together. Those two numbers don't match, not even close. The gravitational mass is several times larger than what the stars and hot gas can account for. Something else is there, the same something that is flattening galaxy rotation curves. It is everywhere, in every structure, at every scale. The accounting works out like this. Ordinary matter, the atoms, the protons and neutrons and electrons that make up everything you have ever touched, represents roughly 5% of the total energy content of the universe. Dark matter accounts for roughly 27%. The remaining 68% is dark energy, a separate mystery, the thing that is driving the expansion of the universe to accelerate. Add it together, and you have a universe that is 95% composed of things that have no confirmed identity. This is the current state of cosmology. It is not a footnote, it is the central fact. What is dark matter made of? The honest answer is that nobody knows. Decades of theoretical work produced a leading candidate, the WIMP, short for Weakly Interacting Massive Particle. A WIMP would have mass, interact gravitationally, interact via the weak nuclear force, and do nothing else that would make it visible. It was an elegant solution. Detectors were built deep underground to shield them from ordinary cosmic ray background, sensitive enough to catch a WIMP if one bumped into an atomic nucleus. 50 years of searching, not one confirmed detection. The WIMP hypothesis is not dead, but it is in serious difficulty. This is where things get stranger. A small group of researchers, Catherine Fries and Martin Winkler at the University of Texas at Austin, have proposed something that sounds almost too bold. What if dark matter was not produced during the Big Bang at all? The ordinary matter we know, the protons, neutrons, electrons, was created in the hot, dense first moments of the universe. The assumption has always been that dark matter formed then too. Fries and Winkler propose a different timeline. A cosmic energy field, existing after the Big Bang, may have undergone a quantum phase transition at some later point. That transition would have released enormous amounts of energy in the form of dark matter particles. They call it the Dark Big Bang, a second creation event, invisible, producing no light, leaving behind only a vast invisible sea of particles that then proceeded to build the scaffolding on which the entire visible universe was assembled. The idea cannot yet be confirmed, but it raises a question that makes the standard picture look suddenly fragile. If dark matter was formed separately from ordinary matter, through a mechanism we have not yet identified, in a process that produced no light, then our entire model of the early universe may be missing something fundamental. Dark energy compounds the uncertainty. For decades, it was treated as a constant. The cosmological constant Einstein originally inserted into his equations, representing a fixed repulsive energy inherent to space itself. Recent observations are beginning to suggest that dark energy may not be constant. It may be evolving, growing weaker over time, or changing its character. If that is confirmed, the standard cosmological model, the lambda cold dark matter framework that has organized the field for 30 years, will need to be rebuilt from somewhere close to the beginning. Dark matter has shaped every structure in the universe, from galaxy filaments down to the halos that allowed the first galaxies to form, and we do not know what it is made of, where it comes from, or why exactly that amount of it exists. The universe is not uniformly filled with galaxies the way raisins are distributed through raisin bread. Pull back far enough that entire galaxy clusters shrink to points, and what you see is something nobody predicted before the data started coming in. The universe has structure at the largest scales, not random scatter, not uniform fog, a web. Vast filaments of matter stretching across hundreds of millions of light years, connecting at dense nodes where clusters pile on top of clusters, and between those filaments, enormous spherical regions where almost nothing exists at all. Astronomers call these regions voids, and the word undersells them badly. The cosmic web is not a metaphor. It is a measured, mapped, physical arrangement of matter that emerged from the tiny temperature fluctuations in the early universe, those same ripples recorded in the cosmic microwave background. Gravity spent billions of years pulling matter along those ripples, amplifying small differences until dense regions became denser and thin regions became thinner. The filaments are where matter collected. The voids are what was left behind. A structure this large has no analogy in human experience. The filaments themselves can run for 1 billion light years. The voids between them can be 300 million light years across or more. The Boötes Void is the most studied example, and it is genuinely unsettling. Roughly 330 million light years in diameter, located in the direction of the constellation Boötes, it should by ordinary statistics contain thousands of galaxies. It contains roughly 60. When astronomers first mapped it in 1981, the result was so unexpected that some of them assumed the data was wrong. It was not wrong. There is simply almost nothing there. The galaxies that do exist inside it are clustered near its edges, as though pressed against the walls of a bubble, which is essentially what they are. The interior is as close to true emptiness as the universe gets. What does that emptiness actually consist of? The density inside a cosmic void drops to roughly 1 hydrogen atom per cubic meter. Compare that to the interstellar medium, which manages about 1 atom per cubic centimeter, 1,000,000 times denser. The air you are breathing right now has something like 30 quintillion molecules per cubic centimeter. The interior of a void is not just sparse by human standards, it is sparse by the standards of deep space itself. Pressure falls so low that the concept almost loses meaning. This is the floor of emptiness that the universe actually offers. The temperature inside a void pulls toward the 2.7 Kelvin baseline of the cosmic microwave background, but it does not quite reach it. The small amount of ionized gas scattered through even the emptiest regions absorbs and re-radiates energy, keeping the temperature fractionally higher than the CMB alone would produce. The difference is tiny. It is not a warm place by any standard, but it is not perfectly cold either, because perfect cold does not exist anywhere the CMB can reach, and the CMB reaches everywhere. Here is something worth sitting with. Even these voids are not truly empty. The cosmic web does not simply stop at the filament edges and leave the voids as blank nothing. The web continues at lower and lower densities, threading even the emptiest regions with structures too thin to detect easily. And dark matter halos extend throughout the void volume, invisible scaffolding that ordinary matter is too sparse to trace. What appears empty to a telescope sensitive to light is still threaded with whatever dark matter actually is, distributed in the same web pattern, but at densities below the threshold of current detection. The voids are the quietest rooms in the universe, not sealed chambers. Imagine a spacecraft sitting in the center of the Boötes Void. What would the crew actually see? In every direction, darkness. Not the darkness of a clear night sky with stars. Actual darkness, with the nearest galaxies so far away that they would be faint smears at the limits of visibility, not points of light, but suggestions of light. No nearby stars, no nebulae, no structure. The cosmic microwave background would be there, as it always is, a faint bath of microwave energy arriving equally from all directions, undetectable to human senses but measurable with instruments. The experience would be indistinguishable from traveling through ordinary intergalactic space, because there is nothing around to mark the difference. The void does not announce itself, it simply continues. The numbers involved stop being fully processable at some point. From the center of the Boötes Void to the nearest galaxy is roughly 150 million light-years in any direction. A signal sent toward that galaxy at the speed of light would travel for 150 million years before arriving. The universe itself is only 13.8 billion years old, which sounds large until you realize that the round trip from the center of this void to the nearest galaxy and back takes more than 2% of the entire current age of the universe. Nothing we could build would make that journey. Nothing we could build could come close to making that journey. And yet, even accounting for that, the Boötes Void is not exceptional. There are dozens of voids of comparable size mapped so far, and the mapping has covered only a fraction of the observable universe. The cosmic web extends in all directions to the edge of what we can observe, and the voids between its filaments are everywhere. The universe built itself this way, not despite the physics, but because of it. Gravity is efficient. It clears out the regions between structures and packs matter into walls and filaments, leaving vast hollow spaces that span distances light takes hundreds of millions of years to cross. In the center of the Boötes Void, with the nearest galaxy 150 million light-years away in every direction, the observable universe would contain so few stars that the night sky would be darker than anything we can achieve with the most light pollution-free location on Earth. The only human-made objects in interstellar space are two spacecraft launched before most of the people currently alive were born. Voyager 1 left Earth in September of 1977. Its primary mission was the outer solar system. It flew past Jupiter in 1979 and Saturn in 1980, sending back images that rewrote what planetary scientists thought they knew. Then it kept going. There was no off switch, no reason to stop. The same velocity that carried it past Saturn carried it outward, year after year, decade after decade, through the cold dark beyond the planets, past the boundaries of anything a human being had ever explored. For 35 years it travelled. Then, in 2012, something changed in the data. The instruments aboard Voyager 1 registered an abrupt shift in the plasma surrounding the spacecraft. The density changed, the temperature changed, the particles were different. The flux of galactic cosmic rays, those high-energy particles streaming in from deep space, jumped sharply. For years, scientists had been watching the numbers inch toward this moment, debating exactly when the crossing had occurred. The 2012 data settled it. Voyager 1 had crossed the heliopause. It was outside. After 35 years of travel, a machine built with 1970s technology had become the first human-made object to enter true interstellar space. What the crossing confirmed was something that could not be assumed in advance. The heliosphere has a real boundary. The solar wind does not simply thin out forever into nothing. It pushes outward until it meets the interstellar medium, and at that meeting point, it stops. Inside that boundary, the sun's influence dominates. Outside it, interstellar space begins in earnest, with its own plasma characteristics, its own particle environment, its own rules. Voyager 1 crossed from one regime into the other, and its instruments felt every bit of the difference. The numbers involved in Voyager's current position are the kind that resist comprehension. The spacecraft is approximately 24 billion kilometers from Earth. A radio signal traveling at the speed of light takes about 22 hours to make the trip one way. When engineers at NASA's Jet Propulsion Laboratory send a command to Voyager 1, they wait nearly 2 days for it to arrive, and then nearly 2 more days for any response to return. Every communication is a 44-hour round trip across a silence so vast it is difficult to hold in the mind. What makes this stranger still is the machine doing the communicating. Voyager 1 is roughly the size of a small car. Its onboard antenna, the dish it uses to reach Earth across 24 billion kilometers, transmits at a power level weaker than a cell phone signal. The spacecraft runs on a radioisotope thermoelectric generator, a device that converts heat from the radioactive decay of plutonium-238 into electricity. By now, decades into its journey, that generator produces less power than a standard household light bulb, and yet the signal gets through. Engineers on the ground, using large dish antennas and careful data processing, can still pull coherent scientific information from a machine launched 47 years ago, running on the equivalent of a dim, incandescent glow, screaming across the void with less radio power than the device in your pocket. This is one of the more quietly remarkable facts in the history of human engineering. Not spectacular in the way a rocket launch is spectacular, remarkable in a slower, deeper way, the kind that settles in when you actually think through what is happening. A civilization built a machine, threw it outward, and then kept talking to it for nearly half a century as it crossed into territory no object from Earth had ever entered. Voyager 2 made the same crossing in 2018, entering interstellar space through a different part of the heliopause. Its instruments were still functioning at the crossing, and the data it returned from that region confirmed and extended what Voyager 1 had found. The heliosphere is not a perfect sphere. The boundary varies depending on direction, shaped by the interstellar medium pressing back against the solar wind from outside. Both spacecraft measured that boundary from different angles, and together they began building the first direct picture of what lies immediately beyond the sun's reach. Beyond that picture, though, the probes cannot go, not on any human timescale. The interstellar space Voyager 1 now moves through is not the deep interstellar medium of other star systems. It is the very near neighborhood of the sun, still local, still within the extended gravitational reach of the solar system's outer objects. The nearest star system, Alpha Centauri, sits roughly 4.2 light-years away. Voyager 1, moving at about 17 kilometers per second, would close that distance in approximately 73,000 years. No one who built the spacecraft will be alive. No nation that funded the mission will exist in any recognizable form. Bolted to Voyager 1 is a gold-plated copper disc, a record containing sounds and images selected to represent Earth and its inhabitants. Music, spoken greetings, the sound of rain, the sound of surf, brainwave recordings from a human being thinking. It was addressed with complete sincerity to whatever intelligence might one day find it. At its current speed, Voyager 1 would need 73,000 years to reach the nearest star system, which means the golden record it carries, addressed to whoever might find it, is going to be in transit for longer than all of recorded human civilization has existed, multiplied by more than 10. Step back from all of it. The vacuum, the radiation, the neutron stars, the voids. And the thing that stands out is not how much we know, but how thin the margin of known is against what we do not. The observable universe spans 93 billion light years. That number is almost impossible to hold in your mind, yet it represents only the portion from which light has had time to reach us. Beyond that horizon, the universe keeps going. Some models suggest it goes on effectively forever. We will never know. The expansion of space carries those regions away faster than light can cross the growing distance, and no telescope, no matter how powerful, can fix that. The information simply does not arrive. What lies past the cosmic horizon is not hidden. It is gone. Within the part we can see, the situation is stranger still. Roughly 95% of everything that exists comes in forms we cannot directly detect. Dark matter, dark energy. The labels are honest about how little they contain. We name these things after what they are not ordinary matter, not known energy, the 5% we can actually observe. The stars, the gas, the dust, the galaxies is a thin skin on something we do not understand, and that thin skin itself is only partially mapped. The full picture is incomplete. Every year, thousands of supernovae go off in distant galaxies, and no instrument catches them. Exotic transients flare and fade without a single telescope pointed in the right direction. Black holes merge, magmatars release bursts, neutron stars collide. Most of it happens unobserved, unreported, unnamed. The universe is not holding still while we catch up. Then there is the interior of a black hole, the most complete information blackout in physics. General relativity predicts a singularity, infinite density, zero volume, and then stops. The equations break down. Whatever happens at that point requires a theory of quantum gravity that does not yet exist. We have been building toward it for a century. We are not there. The deepest question deep space poses is not about distance or temperature or radiation. It is about whether the physics we have is sufficient to describe reality. So far, the answer appears to be no. The nature of the dark matter particle is unknown. We have been searching for it directly for roughly 50 years with no confirmed detection. The nature of dark energy is unknown. Recent observations suggest it may be evolving rather than constant, which would break the standard cosmological model. The origin of the cosmic asymmetry between matter and antimatter is unknown. Why is there something rather than nothing remains, technically, an open question? And none of this accounts for what we have not yet thought to ask. Every major shift in astronomy came from something unexpected. A persistent hiss in a radio antenna that turned out to be the afterglow of the Big Bang. A clockwork signal in a radio telescope that nearly got filed as extraterrestrial contact before it was identified as a pulsar. A star dimming in a way that broke every existing model. The pattern is consistent. The universe keeps producing things that were not in the textbook because the textbook was written before we looked closely enough. Deep space is not a backdrop. It is not a void waiting to be crossed. It is an environment with physics we are still learning, matter we cannot see, energy we cannot explain, and boundaries we cannot reach. The universe has been here for 13.8 billion years, and will be here for trillions more. And if the history of astronomy has taught us anything, it is that whatever we think we are missing, the actual answer is going to be stranger than the question.